What's up? I'm Vin, and today I want to go through this AP Calculus AB BC Unit 4 practice test, and I'll leave a link to a copy of this test in the description below. So first up here, we have section 1, the multiple choice, and calculator use is not permitted. Question 1, we have a cup of coffee, and the function C of t is a differentiable function that tells us the temperature of the coffee, and we're told that C prime of 4 equals -6. And we want to know which of the following statements is definitely true about the coffee's temperature 4 minutes after it was poured. So for this question, the big idea is that the derivative C prime of t tells us the instantaneous rate of change of C of t. So if we use this idea to go through the answer choices, we could see choice A is no good because this is saying that the temperature of the coffee has decreased by a total of 6 degrees Celsius in the first 4 minutes. So this would tell us how much the temperature dropped in 4 minutes, not exactly how fast it's dropping at an exact moment in time. That's what we mean when we say the instantaneous rate of change. So that's how we know choice A is no good. If we look at choice B, the temperature of the coffee is decreasing at a rate of 6 degrees Celsius per minute at t equals 4 minutes. This answer choice is looking good. And this $1 million phrase right here, we have that the temperature of the coffee is decreasing. And we know that the temperature of the coffee is decreasing because C prime of 4 is equal to -6. Okay, so anytime our derivative comes out negative here, that means our function C of t in this case is decreasing. So that's how we know choice B is good. Choice C is no good because it's saying the temperature of the coffee is 6 degrees Celsius at t equals 4. That's no good. That would be true if we had something like, let me just write this out nicely. If we had C of 4 is equal to 6, then choice C would be true, but that's not what we were given here. We were given C prime of 4 equals -6. And then choice D is almost good, but it says the coffee's temperature is increasing at a rate of 6 degrees Celsius per minute at t equals 4 minutes. So that would be true if C prime of 4 was equal to +6. But that doesn't make sense. If you pour coffee on, into a cup on your countertop, the coffee's not going to get hotter once you pour it into a room unless the room is like insanely hot, and then you're probably not going to want to drink a cup of coffee anyway. But in either case here, choice B is our solution. Question 2, we have a cylindrical tank with a radius of 5 meters and a height of 10 meters, and it's being filled with water. And the water level is rising at a constant rate of 0.4 meters per minute. And we want to know which of the following statements is true when the height of the water is 3 meters. So for this question here, we just have to think about what's going on. So we have this cylindrical tank here, and it's being filled with water. But one thing to be mindful of is that the tank itself is not changing. So the radius of this tank is 5 meters, and the height of the tank is 10 meters. But what we have to think about is that as the water fills this tank, the water level is changing. Okay, so as the water fills this tank up, the water level is rising, but there is one part of this that's remaining constant the whole time. The radius is not changing as the water level rises. Okay, so the height, we can put a variable here because once again, as the water goes in, the water level rises, but the radius here is not changing when we're looking at this tank from the inside. So what we have is, in general, the volume of a cylinder is pi r squared times h. But if we talk about the volume of water, then this is a different scenario because once again, if we look at the water on the inside, the radius is not changing at all as the water fills up this tank. So we could set r to be equal to 5 meters. So let's go ahead and plug in. We're going to have r is equal to 5. That's not changing. And that's going to give us the volume of water is pi times, we have 5 squared, and then times h. So the formula we have is volume equals, and we're going to have 25 times pi. So we have 25 pi, and then times h. So now we're going to look at here the rate of change of the volume of water. So let's go ahead and find the derivative with respect to time. And we're going to have on the left side here, the derivative with respect to time of v is dv over dt. And this is equal to, we have 25 pi times the derivative of h is dh dt. So now let's plug in. We're going to have dv dt. And we're looking at the rate of change of the volume at the moment when the height is 3 meters. So at h equals 3. And when we plug in here, and I'll write the units out at the very, very end, we're going to have 25 times pi. And notice that there's no variable h to replace here, but we do have to replace dh dt. And that information was given to us over here. They told us the water level is rising at a constant rate of 0.4 meters per minute. So that means that dh dt is equal to 0.4, and we have meters per minute like this. So if we plug in here, we're going to have times 0.4. And since we're talking about the rate of change of volume, the units would be cubic meters per minute, since volume is 3 dimensions. And now we could just multiply here. If you want to do this mental math, just imagine that you're doing 25 times 4 instead. 25 times 4 is 100. So if we do 25 times 0.4, that would just give us 10. So we would have 10 pi, and then the units here would be cubic meters per minute. And what this means is the rate of change of the volume is equal to 10 pi cubic meters per minute. If we scan the answer choices here, we could see that the volume of the water in the tank is increasing at a rate of 10 pi cubic meters per minute when h is equal to 3 meters. So choice D is our solution. Question 3, we have the function b of t is used to model the population of bears in a specific forest region over the next 20 years. And b of t is the projected number of bears in the forest t years from now. And then we have, according to the model, which of the following gives the rate at which the bear population will be changing at t equals 7. So for this question here, we have to know that the rate of change at an exact moment of time refers to the derivative. So b prime of t is going to tell us the rate of change of the population of bears at exact moments in time. So if we want to know what is the rate of change of the bear population at t equals 7, that's just b prime of 7, which matches choice C. Now, the problem with choice A is no good because b of 7 represents the number of bears. So this is the number of bears at t equals 7 years. Okay, so this would tell us the exact population at t equals 7. And now the problem with choice B is that this is telling us here the average rate of change of the bear population. Okay, so the average rate of change of b of t, the bear population, on the interval from 0 to 20. So that's why this answer choice is no good. And then choice D is no good because this tells us the average rate of change of the bear population on the interval from 0 to 7. So this is no good. Once again, we're looking for the instantaneous rate of change. We'll just make that a little bit neater. We're looking for the instantaneous rate of change, so we're going with b prime of 7. For questions 4 through 6, we have this graph of a velocity function, and it's modeling the velocity in meters per second of a particle at time t along a horizontal axis. So for question 4, we want to know on which interval or intervals is the particle moving to the right. So anytime you're looking for when a particle is moving to the right, you're going to be thinking about when is the velocity function greater than 0, because when velocity is greater than 0, what I'm thinking about here is we have movement to the right. So if I have a particle here, this is when it's moving to the right, when velocity is greater than 0. When velocity is less than 0, no matter where the particle is, it's going to be moving to the left like this. If we were talking about vertical motion, so along a vertical axis, positive velocity would mean that the particle is moving up. Okay, so in the vertical direction, when we have a particle with positive velocity, it's moving up, and then negative velocity would mean that the particle is moving down like this. So what we have to look for is when is the graph of velocity greater than 0, and that means when is it above the horizontal t-axis here. So notice that the graph is above the t-axis from 0 to 1 and then from 3 to 4. So we just scan the answer choices here. We could see that choice D is our solution. One answer choice we have to be very careful of is choice B. Choice B is a very dangerous bear trap. So if you look here from 2.3 to 3.3, yes, this graph here is going up like this. However, that means that the particle is accelerating at this time. It has positive acceleration because notice here, if we look at the slope of the tangent line here, that the slope of the tangent line here is positive. So that would tell us at, let's say, something like 2.5. This tells us that the acceleration at 2.5 is positive because the slope of the line tangent to the velocity curve is positive there. But that's a common mistake here. Just be very careful. We're looking for when velocity is greater than 0, so we're going with choice D. Question 5, what is the greatest speed the particle reaches on the interval from 0 to 5? So for this question, it's very tempting to say 5 meters per second. 5 meters per second is a very dangerous bear trap, okay? Don't just look for the highest point on the graph. You have to remember that speed is equal to the absolute value of velocity. So that means we also have to consider the lowest point on the graph from 0 to 5. And the lowest point occurs here. And notice that if we take the absolute value of negative 20 and we say meters per second here, this tells us the speed of the particle at this moment is equal to 20 meters per second. And notice that 20 meters per second is greater than 5 meters per second. So choice D would be our solution. Question 6, we want to know at what time or times t on the interval 0, 5 does the particle change direction? So when you're looking for when the particle changes direction, you're looking for when does the velocity change signs. Okay, so we're looking for when does velocity change signs. And for this, we could find right from the graph. So if we look over at the graph here, you can notice here that we have three roots. We have a root at t equals 1, at t equals 3, and at t equals 4. And if we analyze the root of the velocity curve here at t equals 1, notice that the velocity changes from positive to negative at this location because it goes from being above the t-axis to under. And then if we notice over here at t equals 3, velocity changes from negative to positive here. It goes from under the graph to over. And then at t equals 4, velocity changes one more time from positive to negative. So this tells us that we have three sign changes in the velocity graph, which means that the particle is going to change directions 3 times at t equals 1, at t equals 3, and at t equals 4. Question 7, we have a ladder sliding away from a wall related rates question. So the first thing I would do is just draw this out. So I'm just going to go ahead and draw out a right triangle here. And we're told that the ladder is 15 feet. So here's the ladder, and it's leaning against the wall. So the wall I'm going to label here with the Y, and the ground I'm going to label with an X. And they're telling us that the bottom of the ladder is sliding away from the wall at a rate of 2 feet per minute. So what they just told us here was that dx dt is equal to, we have 2 feet per minute. And then after this, what we have is, we want to know how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 9 feet from the wall. So if we want to know how fast the top of the ladder is sliding down, we're looking for dy dt. Okay, so this is what we want to find. So now for these kind of questions with related rates, we want to think of an equation that connects everything. So the Pythagorean theorem will connect these three terms here. We have x squared plus y squared is equal to 15 squared. Now, the reason why we don't have to put a variable for this is because the hypotenuse represents the ladder, and this isn't a magic ladder, okay? The ladder is going to stay fixed at 15 feet, so we could just leave this part here constant. All right, so now we could simplify this a bit. This is x squared plus y squared equals, we have 15 times 15 is 225. And now for this, what we're going to do is we're going to take the derivative with respect to time. Just know for these related rates questions, it's very important that you set up the correct equation, because if you mess up at this step, then the whole question just falls apart right away. So now we're taking the derivative with respect to time, and this is where our background in implicit differentiation comes in. We have to be skilled with implicit and the chain rule here. So when we take this derivative, the derivative of x squared, we have to be careful. We're not just going to say 2x. We're going to have to tack on dx dt. And the reason being is that we're taking the derivative with respect to time, and that doesn't match the variable x. So then next we have plus the derivative of y squared is 2y, and then we have dy dt. And then this is equal to the derivative of 225 is 0. And now the next thing we could do is solve for dy dt, because that's the rate that we're looking for in this question. So what we could do is we're going to do some algebra. We're going to move the 2x dx dt over to the right. We're going to subtract it on both sides. So that's going to give us in the next line here, we're going to have 2y dy dt equals, and then we have negative 2x dx dt. And now what we're going to do from here is just divide both sides by 2y. And notice what we have. We have 2y over 2y canceling. 2 over 2 cancels. And this tells us here, I'll write it over in this location. We have dy dt is equal to, we have negative x dx dt divided by y. So now we have to think about what are each of these pieces. So dx dt is 2 feet per minute. And they're telling us what is the rate of change when the bottom of the ladder is 9 feet from the wall. So the bottom of the ladder is here and the wall is over here. So that's when x is equal to 9. So eventually what we're going to do is we're going to plug in x equals 9. But what we have to know is what is the corresponding y value the moment that x is equal to 9. So we have x equals 9. We have the hypotenuse is 15. And what I'm thinking of here is I'm thinking of a 3, 4, 5 triangle. Okay, so I'm thinking of this triangle here. We have a 3, 4, 5. And I'm not drawing this to scale when I'm thinking about it here. So we have 3, 4, 5. And if I do 3 times 3, I get 9. If I do 5 times 3, I get 15. So 4 times 3 is going to give me 12. And that's located in the y spot. So we have y is equal to 12. We could just do Pythagorean theorem to solve for the y value here, but it's just much easier to use similar triangles. So now we have dy dt the moment when x is equal to 9 and y is equal to 12. So we plug in here and we're going to have negative, and then we have x is 9. Dx dt is 2 feet per minute, but we'll leave the units out. We'll just write everything at the end. So we have minus 9 times 2 over y is equal to 12. And now if we simplify here, we could divide the top and bottom by 2, and that's going to give us, we're going to have 1 on top over 6 on bottom. And if we divide the top and bottom by 3, negative 9 over 3 is going to give us negative 3. And when we divide 6 by 3, we get 2. So this is going to work out to -3/2. So now we look at the answer choices here. They're asking us how fast is the top of the ladder sliding down the wall. So we just have to match up the value here with choice B, 3/2 feet per minute. Remember, the units here, where are the units coming from? dx dt was 2 feet per minute. So if I write the units next to it like this, that's why at the end we're getting feet per minute. Now, if this is throwing you off, like why is this negative and this is positive? Well, when dy dt is negative, that means y is decreasing, which makes sense because as the ladder falls down, as it slides down the wall, y is shrinking. But they're asking us how fast is the top of the ladder sliding down? So since they indicated the direction in the question itself, we're sliding down at a rate of 3/2 feet per minute. If they just said, what is the rate of change of y, then we would include the negative with it. But choice B in this case is going to be our solution. Question 8, we have a giant bear 3 meters tall walks directly away from a street light that is 5 meters above the ground. If the bear is walking at a constant rate and the bear's shadow is lengthening at a rate of 3/5 meters per second, at what rate is the bear walking? So this question involves a similar triangles concept. The first thing I would do is label the diagram. So we have the bear is 3 meters tall, so I'll just write a 3 here. The street light is 5 meters tall, and then we have that the bear is walking away from the street light. So we're going to call this distance here x. That's the distance from the bear to the street light, and then y is the length of the bear's shadow. So what we could do with this information is we could extract two triangles here. So I'm going to call this here, this is our big triangle, and the dimensions here are going to be 5, and then we would do x plus y to find the base here. And then our little triangle is going to be built by the bear and his shadow. And this little right triangle here, the height of the triangle is going to be 3, and the base is going to be y. And I know that these triangles are similar because they both have a right angle, and they are sharing a common angle over here. So they have angle-angle similarity, and since we have similar triangles, the ratios of their corresponding sides are going to be in proportion. So that allows us to set up on the side here, we could say 5/x plus y is equal to, we have 3/y. And now we could just do the algebra here. We could cross multiply, and we're going to have 5y is equal to 3x plus 3y. But now let's think about what our goal is here. We want to find at what rate is the bear walking. So that's going to affect the x variable. We want to know what is dx over dt in this case here, because once again, the rate at which the bear walks affects x over here. That's how fast it's moving away from the lamppost, so, or the street light here. So then what they told us, the rate of change of the bear's shadow, the rate over here, 3/5 meters per second, that represents dy dt. So we could say dy dt is equal to, we have 3/5 meters per second, because once again, that's affecting the variable we labeled over here that's representing the length of the bear's shadow. So what that tells me, if we want to find dx dt, I'm going to solve this equation for x. So I would start here by subtracting 3y on both sides. And if we do minus 3y on both sides, we're going to have 3x is equal to, we have 2 times y, and then solving for x, we're just going to divide both sides by 3. And that tells us that x is equal to, we have 2/3 y. So now from here, what we could do is we could take the derivative with respect to time of both sides of this equation, and that's going to give us dx dt is equal to, we have 2/3, the derivative of y is dy dt. So if the bear is walking at a constant rate, that means that the shadow is also lengthening here at a constant rate. So then all we have to do to find dx dt is we're going to plug in the rate of change of the shadow. So we're going to have dx dt is equal to, we have 2/3 times dy dt is 3/5 meters per second. And now we just simplify 3/3 cancels, and we'll write the result over here that dx dt is going to be equal to, we have 2/5 meters per second. So now we could scan the answer choices, but notice that everything's written in decimal form. So if we just think about this here, 2/5, if we multiply the top and bottom by 2, that's 4/10, and 4/10 is going to be equal to, we have 0.4. So we could also say that the solution is 0.4 meters per second, and that's going to match up with choice D. Question 9, we have this right triangle shown below, and we have if theta increases at a constant rate of 2 radians per minute, at what rate is x increasing in units per minute when x equals 12 units? So for this one here, we're going to have to use a trig function to connect these terms here. So we could say that sine of theta is equal to, and we're going to have the ratio of the side opposite of theta. So we have x over the hypotenuse, the side opposite the right angle is 13. So what I'm going to do here, since in a moment we're going to have to take the derivative of this, I'm going to rewrite this. I'm going to say sine theta equals, and I'm going to rewrite this as 1 over 13 times x. So I'm doing this so that I don't have to use the quotient rule on the right side. So now we could take the derivative with respect to time, and this is going to give us on the left side, we're going to have cosine theta times d theta dt. Once again, we have to use the chain rule here because we're taking the derivative with respect to time. So we can't just say cosine theta, we have to tack on this extra piece here. And now on the right side, we're going to have 1 over 13 times the derivative of x is not just 1, it's going to be 1 times, and we have dx dt. So now our goal is to find at what rate is x increasing. So that means we're looking for this piece. We want to know what is dx dt. So one thing we could do to make this look a little nicer is we can multiply both sides by 13, and that's going to get the 1 over 13 to cancel out next to dx dt. So now I'll write the result over here. We have dx dt is equal to, and we have 13 times cosine theta times d theta dt. So now what we need to find here, they told us d theta dt. See, over here they told us theta increases at a constant rate of 2 radians per minute. So they told us d theta dt is equal to 2 radians per minute. And I'll leave the units out for now. And that tells us this piece. But we have to know, what is cosine theta? So now we have to think of the rest of the givens here. They're telling us to find all of this the moment when x equals 12 units. So if we look at this right triangle here, now I'm going to plug in x equals 12. So we have x equals 12, the hypotenuse is 13, and this is one of our Pythagorean triples. We should know here that the missing side here is 5. And if you needed to check, you could just do 5 squared plus 12 squared, and I promise that it's equal to 13 squared like this. So theta is over here. So now when we want to find what is cosine theta, if we use this reference triangle here, is equal to the ratio of the side adjacent to theta, which is 5, over the hypotenuse is 13. So now we could just plug everything in. We could say dx dt is equal to, we have 13 times cosine theta is 5 over 13, and then we're multiplying by d theta dt, which is equal to 2. So now we just cancel everything out here. 13 over 13 cancels, and we could simplify. We multiply 5 times 2, and we're going to get 10. So dx dt, x is increasing at a rate of 10 units per minute here. So where the unit of time is minutes. But once again, the answer choices don't have the units. We just need the value. So choice B. Question 10, we have the differentiable function f of x, where f of 3 is equal to 7 and f prime of 3 is equal to 4. And we're going to use local linearity to approximate f of 3.05. So the concept behind this question is we have some function f of x, and all we know is that f of 3 is equal to 7, and we know that f prime of 3 is equal to 4. So that tells us that the slope of our tangent line at x equals 3 is equal to 4. So we don't know what f of x looks like, but let's say I just draw something like this. So now that we have this sketch, we could just visualize here the goal is to approximate f of 3.05. So we want to come up with an approximation for this function value over here. So what we're going to do here is write the equation of the tangent line at x equals 3, and we're going to plug x equals 3.05 into our tangent line equation. And that's going to give us an approximation of the actual value over here. So that's the idea, once again, behind this question. So what I'm thinking of is, what is the point slope form equation of a line? And that formula, we have y minus y1 equals m times x minus x1. So the point is the point they give us over here, f of 3 equals 7. So that's going to be the point we use. That's going to be our x1, y1. And then the derivative here tells us the rate of change of our tangent line. So this is representing our slope in the formula. So now we just plug everything in. We're going to have y minus 7 is equal to, we have 4 times, and then we have x minus 3. So now what we could do from here is just solve for y. So we could add 7 to both sides, and we're going to have y equals 4 times x minus 3, and then plus 7. So now we have the equation of our tangent line. So to approximate f of 3.05, all we're going to do is plug x equals 3.05 into this expression on the right here. So we have 4 times, and we have 3.05 minus 3, and then plus 7. So this is going to give us 4 times 3.05 minus 3 is 0.05, and then plus 7. So now for this part, all I'm thinking of, since we don't have a calculator, is we have 4 times 5 is equal to 20. So if I do 4 times 0.05, I take 20 and I just move the decimal over 2 places. So that would give us 0.20. So we're going to be doing 7 plus 0.20, and that's going to give us 7.20, and this is going to match up with choice A. Question 11, we have the function f of x, and we're told that f prime of negative 2 equals 2, and f of negative 2 equals 5. And then we have, using a local linearity approximation near x equals negative 2, which x value will yield an approximation for f of x of 5.5. So this time around, we're still going to be writing the equation of a tangent line, but this time we're going to set the y value equal to 5.5 and solve for the x. So first, let's write the equation of our line. So the point is negative 2, 5. That's the point they gave us. This is our x1, y1. And then we have a slope here of positive 2. So now we just plug into the point slope form equation, and we're going to have y minus 5 equals, the slope is equal to 2. And then we have x minus negative 2. So I could write minus minus 2, or I could just say x plus 2 like this. So now I'm going to add 5 to both sides. We're going to have y equals, and we have 2 times x plus 2, and then we have plus 5. So we want to know, when will we get an approximation for f of x of 5.5? For which corresponding value of x? So now we're going to set y equal to 5.5. So we'll have 5.5 is equal to, and we have 2 times x plus 2, and then plus 5. So now we could subtract 5 on both sides. And this is going to give us, we're going to have on the left side, 5.5 minus 5.0 is going to give us 0.5 equals, and now we have 2 times x plus 2. And now at this step, what we could do is we could divide both sides by 2. And now we have 2 over 2 canceling, and we're going to have x plus 2 is equal to, and if we do 0.5 divided by 2, that's going to give us 0.25. And now just subtract 2 on both sides. And now we just have to think carefully here. X is equal to, and if we do 0.25 minus 2, that's going to give us negative 1.75. And this is going to match up with choice B. Question 12, we're going to have to use L'Hopital's rule. And if this was the free response section of the test, in order to properly state that we're using L'Hopital's rule, we would have to say in this case here that the limit as x approaches pi over 4 of our numerator, so g of x minus g of pi over 4, is in this case equal to the limit as x approaches pi over 4 of our denominator, where we have sine of x minus sine of pi over 4. And notice that both of these limits are equal to 0. So this is a situation where we have the indeterminate form 0 over 0. Okay, just know if you were to say on the AP test in the free response, this equals 0 over 0, they would take away a point for notation. So you could think 0 over 0 and say indeterminate, but don't write something like this in the free response. But for the multiple choice, it doesn't matter. But just know this part here would be if we were answering this in the free response part of the test. Since this limit of the top equals the limit of the bottom equals 0, this means that L'Hopital's rule applies. So now what we're going to do is we're going to apply L'Hopital's rule here, and we're going to take the derivative of the top, and we're going to get g prime of x. Now, technically, g of pi over 4 is equal to 2, and when we take the derivative of a constant, it's equal to 0. So we're not going to have anything after the subtraction sign. And now the derivative of the bottom, we're just going to get cosine x, because once again, sine of pi over 4 is a constant, and we're taking the derivative of a constant that's equal to 0. So now this we evaluate by plugging in, and we're going to have g prime of pi over 4 over cosine of pi over 4. Now, one thing to mention here, they told us that g of x is a differentiable function. So that means we're not going to run into any trouble when we take the derivative and find g prime here and evaluate it at pi over 4. So now we just use the value that they gave us. They told us g prime of pi over 4 is equal to 3, and then cosine of pi over 4 is equal to square root 2 over 2. So if we simplify this, this becomes 3 times 2 over square root 2 if we use keep, change, flip, and then this will give us 6 over square root 2. And now notice this answer choice does not show up, so you should rationalize the denominator, and this will simplify to, we have 6 square root 2 over 2, and then 6 divided by 2 is 3, so we get 3 square root 2, and this is going to match up with choice D. So for question 13, we're not going to worry as much about notation, so I'm just going to say this is poor notation if we write it like this, but it's multiple choice, and you're not graded based on your notation. So if we were to plug in 0, we're going to get e to the 0 minus 2 times e to the 0 plus 1 over 0 squared. And notice that this gives us on top, we have 1 minus 2 plus 1 over 0. And this gives us 0 over 0, which is an indeterminate form, which means L'Hopital's rule can be applied. So now we apply L'Hopital's rule, and we're going to have the limit as x approaches 0 of, and just remember this chain rule variant. When we take the derivative of e to a constant times x, it's equal to the constant times e to the kx. So the derivative of e to the 2x, we're going to have 2 times e to the 2x. And then we have minus 2 times the derivative of e to the x is e to the x, plus the derivative of 1 is 0. Over, and then we take the derivative of the bottom and we get 2x. But notice if we plug in 0 again, we're going to have 2 times e to the 0 is going to give us 2 times 1 minus 2 times e to the 0 is going to give us 2 times 1 is 2 over 2 times 0 is 0. So we get 0 over 0 a second time. So this means we have to use L'Hopital's rule once more. Okay, so this is going to give us, we have to use 2 rounds of L'Hopital's rule here. So now we're using the chain rule again. The derivative of e to the 2x is still 2e to the 2x, but we're multiplying by the 2 in front. So we're going to have 2 times 2e to the 2x like this, minus the derivative of 2e to the x is 2e to the x. And now we're dividing by the derivative of 2x is 2. So now when we plug in 0, notice we have 2 times 2 is 4, so we have 4 times e to the 0 minus 2e to the 0 over 2, and e to the 0 is equal to 1, so we're going to have 4 minus 2 divided by 2, which gives us 2 divided by 2, and that's equal to 1. So this is going to match up with choice B. Question 14, we have this position function x of t, and we're told that m, n, p, and q are constants, and we want to know which of the following could represent a of t, the acceleration of the particle at time t. So the big idea for this question is knowing that when you have the position function, if you take the derivative of position with respect to time, that's going to tell you the velocity function. And if you take another derivative with respect to time, that's going to tell you the acceleration function. Okay, so the derivative of position is velocity, and the derivative of velocity is acceleration. So that tells us that acceleration is equal to the derivative of velocity, but it's also equal to the second derivative of position. So for this question, what we're going to do is we're going to take 2 derivatives of this function. And one thing to be mindful of, the chain rule step here gets a little bit annoying. You have to know that when you're doing the chain rule for something like, let's say, sine of kx, this is going to be equal to cosine of kx, where k is constant, and then the derivative of kx is k. And the chain rule variant for cosine of kx is going to give us something like this. We're going to have minus sine of kx, and then the derivative of the inside is k. All right, so that's the idea we're using for this question. So the velocity function, we're going to take the first derivative of this function here, and we're going to have m times the derivative of cosine is going to give us minus sine. So I'll just make space here. I'll say minus, we have m times sine of nt. But notice they told us here that n on the inside is a constant. So the derivative of nt is n. So that's just going to go in front like this. And then we're going to have plus p times the derivative of sine is cosine, and then on the inside we have qt, and then the derivative of qt, we're using this chain rule variant here, is q. So that brings us to this step. But now we have to do one more derivative. So we're going to have the acceleration function as a function of time is equal to, so the constants in front, we're going to leave those alone. So we're going to have minus m times n, and now the derivative of sine nt, we're using this chain rule variant, is going to give us cosine of nt. So let's just write this properly. So we have n times t, and then the derivative of the inside is n. So I have n times n in front. So in the next line, I'm just going to call this minus m times n squared, and then cosine nt like this. And now for the next piece, we have plus pq times the derivative of cosine is minus sine. So I'm going to write a minus first. We have minus pq, and then we have sine of qt, and the derivative of the inside is q. So I'm going to put another q in front. So this simplifies to minus p times q squared sine of qt. So this is our acceleration function. So now all we do is scan the answer choices here, and we're going to see that this matches up with choice A. Question 15, we have a table of values for differentiable function f of x, and we want to know, based on these values, what is likely to be the best approximation to f prime of 3. So if we visualize what's going on here, let's look over here at this graph, and we're in the neighborhood of x equals 3, and we'll pretend f of x looks something like this, which is reasonable because these y values are going up. And what we're trying to approximate is f prime of 3, which is the slope of the tangent line at x equals 3. So to get the best approximation possible, what we want to do is we want to pick the values of x that get as close to 3 as possible. So that would be these two x values here at x equals 2.9 and at x equals 3.1. So if we look over here on the graph at x equals 2.9 and at x equals 3.1, what we're doing is we're going to find these points here on the curve that's given to us in the table, and we're going to find the slope between these 2 points and see that the slope of this line in blue is going to be pretty close to the slope of this line in pink. Now they're saying what is likely to be the best approximation, because anything could happen with this function from 2.9 to 3.1. This function could all of a sudden start going way up and way down like this, but that's why they're saying what is likely to be the best approximation. They're pretending that the graph is behaving reasonably on its way from 2.9 to 3.1. So now we're going to say here that f of 3 is roughly equal to, we're going to have f of 3.1 minus f of 2.9, and we're going to divide by 3.1 minus 2.9. So now we just plug in from the table. F of 3.1 is 9.6, and we're subtracting 8.4. That's the value of f of 2.9. And we're dividing here by 3.1 minus 2.9 is 0.2. So now I'm just imagining 96 minus 84 is 12, and I just put a decimal in between. So we have 1.2 over 0.2. And then here you can multiply the top and bottom by 2, and it gives you 12 divided by 2. And that's going to simplify to 6. So the best approximation based on this table is going to give us here choice D. The best approximation for f prime of 3 is 6. So now we move on to the free response, and calculator use is still not permitted. For this free response question, we have a conical tank that is 12 feet tall and has a diameter at the top of 8 feet. And then we have water is poured into the tank at a constant rate of 2 pi cubic feet per minute. And for part A, what we want to do is we want to write the formula for the volume of the cone in terms of h, the height of the water in the tank. So we have this formula for volume here, but the big idea is that no matter where we are in this tank here, we have at any moment the cross section is going to be a right triangle like this. So if I were to take a slice of this cone and I just go here like this, notice that I'm going to have a right triangle. So that's what I want to look at here. But remember, at any moment here, let's say the water level is at this location, these two right triangles here are going to be similar. So that's going to allow us to set up a ratio in a moment. So one thing I want to do first, though, is notice across the top, the diameter is 8 feet. That means that the radius at the top is equal to 4 feet. So what we have here is the big radius is going to be 4 feet, and the big height here is going to be 12 feet. So now what we look at is that at any moment we could have a radius of r and a height of h. So we could set up the following proportion. We could say that r over h, this ratio is going to be equal to 4 over 12. Okay, and we could do this because these two right triangles here are similar. The big right triangle and the little right triangle are similar because notice that they share a common angle down here. So these two right triangles have angle-angle similarity. So now what I'll do from this step here is simplify this. I'm going to divide the top and bottom by 4 to get 1/3. And now I'm going to solve this equation for r. So we have r over h equals 1/3, and I'll just multiply both sides of this equation by h. And this is going to tell us we're going to have r equals 1/3 h. So now to write the formula for volume in terms of h, now we're just going to make a substitution here. We're going to have volume equals, and we have 1/3 pi, and then instead of r squared times h, we're going to replace r with 1/3 h. So now we're just going to simplify here. We're going to have 1/3 h, and now when we square this, we have 1/3 times 1/3 is 1/9, and we have h times h is h squared, and then we're multiplying by h at the end. So now we could just simplify everything. 1/3 times 1 over 9 is going to give us 1 over 27. And then we have pi times h to the second times h to the first is h to the third power. So here's our formula for the volume of the cone, all in terms of h. For part B, we have when the height of the water is 6 feet, at what rate is the height of the water changing? So for this part here, first we're going to take the derivative with respect to time of the equation we found in part A. So we're taking the derivative of v equals 1 over 27 pi times h to the third. And on the left side here, the derivative of volume, we're going to say dv over dt, since we're taking the derivative with respect to time. And this is going to be equal to, we have 1 over 27 times pi. We're going to leave this alone because this is a constant attached by multiplication. And now we just do the derivative of h to the third, which is 3h squared dh dt. So now we have to remember our goal is to find the rate of change of the height of the water. So we want to know what is dh dt. So now we could just move everything over to one side. So we could divide both sides by 1 over 27 pi, and then we have 3h squared. So we have 1 over 27 pi times 3h squared like this. So this is going on both sides. And now on the right side here, everything's going to cancel out except dh dt. So everything here is just wiping out. And we're going to have dh dt is equal to, and we're going to have dv over dt like this. And then in the denominator here, we're going to have all of this stuff. So now we can just simplify this a little bit. So 3 over 27 simplifies to 1/9. So we're going to have 1/9 pi, and then h squared. So our goal is to find the rate of change of the height when h is equal to 6 feet. So we have at h equals 6 feet. So now we just plug in, and now we have to think about, so let me just draw a separating line like this. So dv over dt, they told us that the water is being poured into the tank at a constant rate of 2 pi cubic feet per minute. So off to the side here, I'm just going to point out that dv over dt, so dv dt is equal to 2 pi, and the units are cubic feet per minute. So these are the units for dv dt. So I'm just going to plug that in. We have 2 pi and then cubic feet per minute like this. And now in the denominator here, we have 1 over 9 times pi, and then h is equal to 6 feet. But now just think about this. If we take 6 feet and we square it, so if we do 6 feet squared, not only are we squaring the 6 to get 36, but we're squaring the units here. So we're going to have 36 square feet. So we're multiplying by 36 square feet like this. And now notice cubic feet divided by square feet cancel out completely, and it leaves us with feet to the first power, or the units now are just going to be feet per minute. So now we could just simplify everything. So we could cancel out pi over pi, and then 36 times 1/9 is equal to 4. So we're just doing 36 divided by 9 is equal to 4. So now all of this is going to be equal to, we're going to be left with 2 over 4, and then we're going to have feet per minute like this. So we have feet per minute. And now we can reduce this if we want. This is going to reduce to 1/2, and then we have feet per minute like this. So this is the rate of change of the height. Now, one thing to point out about the AP test is that if you leave everything unsimplified like we did in this line here, you don't actually have to simplify everything. You could leave it like this as a mess without dividing any common factors out, okay? So just know you won't lose any points. But if you want your answer to look nice, then sure, go ahead and simplify. And the correct answer here, dh dt, when h is equal to 6 feet, is 1/2 feet per minute. For part C, we have when the height of the water is 6 feet, at what rate is the area of the surface of the water changing? So for part C, we just have to know that when we're dealing with a cone, at any moment, if we look at any cross section here going horizontally like this, the cross sections are going to be circles. So if we think about the surface of the water is in the shape of a circle. So when we're finding the rate of change of the area of the surface of the water, we're finding the rate of change of the area of a circle, and the formula is A equals pi r squared. So with this equation here, we're going to take the derivative with respect to time of both sides. And on the left side, we're going to have dA dt. And on the right side, we're going to have the derivative of pi r squared. So we're going to have pi times the derivative of r squared is 2r dr dt. So now to close this out, we're going to make use of the information we found in part A and part B. So we need to know here, what is the radius at the moment the height is equal to 6 feet? So this formula we found in part A, we said that r is equal to 1/3 h. So when h is equal to 6 feet, if we plug into that formula from part A, we could say that r is equal to 1/3 of h. So we're taking 1/3 of 6 feet, which is equal to 2 feet. So we have the value of r we need to plug into this formula here. But we also have to know, what is dr dt? Well, if we take the derivative with respect to time of this equation, so we do the derivative with respect to time of r equals 1/3 h, this is going to tell us here that dr dt is equal to 1/3 dh dt. And notice here that we're at the same level as we were in part B, when the height of the water is 6 feet. So we found in part B dh dt when h was equal to 6 feet, and it was equal to 1/2 feet per minute. So to find dr dt, what we could do is we're just going to plug in here. We're going to have dr dt is equal to 1/3, and we just multiply by 1/2, and then we have feet per minute like this. So now we just simplify this. 1/3 times 1/2 is equal to 1/6. So we have 1/6 feet per minute like this. So now to close this question out, we have the rate of change of the area at the moment when the height is equal to 6 feet is equal to, and we have pi times 2 times the radius we found is equal to 2 feet. So we have times 2 feet like this. And then we're going to multiply by dr dt, and dr dt we found to be 1/6, and then we have feet per minute. So now we just work out all these values here. So we have 2 times 2 is 4 times 1/6. So this is going to be 4/6, and then we have a pi tagging along, and then we have feet times feet is square feet. So we have square feet per minute. And now if we want here, we could simplify this. We could say that our final answer, we could just reduce this fraction, is going to be equal to, we have 2/3 pi square feet per minute. So here is the rate of change of the area at the moment the height is equal to 6 feet.